Hello, everybody. My name is Jason Wampler, and I'm doing something crazy. I'm doing another episode of the Rocket Minute with Jason Wampler. Hey, guys, we're gonna review uh, model rocket motor construction very, very quickly. Um, but before we get into the construction of a model rocket, I want you guys to see something. Um, look down here, and I hope the looking down here part is easy to do. Let me adjust the camera angle so that you can see what exactly is going on. Um, well, I tell you what. Boy, come on, sweetheart. Just this tripod of mine is limited in its ability to do what I really want it to do, but maybe. Come on, sweetheart. Oh, there we go. Okay, so I want. Hmm, let's see. I'm not really ready. Okay, yeah, that's kind of okay. Um, the lighting here is just terrible. Okay, so let me This is almost. It's just looks like lots of fire. Okay. Get some light in here. Um, guys, try not to fall asleep on this one. Um, there's some excellent videos out there on rocket construction. Um, but there's no videos on building motors. I suppose I kind of understand why. But let's I was competing with the camera itself. Um, I want to show you a typical rocket motor. Oh, for goodness sake! Wow, just a terrible illustrator. Um, no, I don't like drawing. I like building. I like actually doing. Um, that's awful. Yeah, let me scrap this because I'm in the process of developing a math equation that describes how rocket motors maintain constant internal pressure. I'm talking about solid fuel rocket motors, and it's interesting. There you go. Move back like that. Um, a little farther away. Okay. All right. Missed the split of the table. Got a folding table. One of these days I might get a real table. Starting to work a new job in Reseda as a mechanic. I like these people. I think I'm gonna stay there for a long time. Make some real money. Get my first book published. Woohoo! Okay, so I'm just going to use a single logo motor grain. This is actual size. It'd probably be a 54 millimeter motor. Um, and just to review too, um, boy, nighttime we have gas. Gas to run the burner stove. You see that? Okay, this is that thin line is the phenolic casing. The X is in the fuel grains itself, and the hollow center. That is um, that is the hollow area of the fuel grain itself. Now, it's a pretty boring illustration. What am I talking about? Here goes. High-powered solid fuel rocket motors. They maintain a constant burn rate because of propellant chemical formulation. I know 7 different chemical propellants. There's basically the sugar fuel, um, There's black powder and there's magnesium fortified black powder. That's 3. There's sulfur and zinc, which is dangerous fuel. That's 4. And there's some dangerous advice out there about zinc sulfur motors. Pure magnesium epoxy potassium nitrate motor, very powerful but very dangerous. I believe that's 5. Uh, Ammonium perchlorate, aluminum, and iron oxide. That's 6. That's the space shuttle booster. The 7th motor I know is called a chromite motor, and it's rather dangerous. It is. Hey guys, you're not gonna see much of me today. Chromite is a dangerous substance. It's it's almost aluminum, an all ammonium perchlorate motor with 20% epoxy, um, 80% ammonium perchlorate, and only 1 to 2% chromite. So it's a 2% over 100 percent motor. I've mentioned this before. If it's 102%, there's no such thing. You just kind of put the percentages back, so that makes the percentages a little bit more complicated because everything's got to fit within 100%. Anyway, those are 7 different types of fuel. So that could be any one of these fuels in this particular fuel grain, which I should probably colorize because it'd be easier to see. Not unlike myself with my good haircut. Anyway, solid fuel rocket motors have a stable burn rate, and it's because of the formulation of the fuel. But high-powered model rocket motors, when we're talking about something beyond an I-200, which is 200 nms, is Newton meters or Newton mass. I'm not sure. 200 nms of total impulse is burn pressure times the amount of time it burns. So total impulse for a rocket motor is always going to be burn time times pressure. So it burns for 5 seconds at 200 nms. That you would have 5 seconds times 200 nm would put you at equals an I-200. I-class 200, they come in 29 millimeter, or the next size up, 38 mm. So there you go. So there, if you see that, and this might be backwards. My God, burn time times pressure is 5 seconds times 200 nm is an I-200. If it's a 29 millimeter motor, it's going to be about roughly 14 inches long, about a foot long. It'll be a big, long motor. Depending on how heavy your rocket is, we'll talk about the total altitude of the rocket. Might take off fast or slow. That's another dynamic to get into their own. We get in that. 29 millimeter times 29 millimeter I-200 is going to be about roughly 12 inches long. A long, thin motor. 38 millimeter motor, it's going to be probably about 6 to 8 inches long. 38 millimeters in diameter, 9 millimeters larger in diameter than 29 millimeter motor. Both standard solid fuel model rocket motor sizes. So, and I'm happy for those standards too, because you can count on them. They're constant. Okay, but let me ask you a question. Why is it, and I've always wondered this question, why is it that solid fuel rocket motors burn at a constant pressurized rate? Well, because of the fact that most solid fuel rocket motors in high power experimental rocketry, even in sounding rockets, even in the space shuttle boosters, which have polygon snowflake cores, the ones that generated 4 million pounds of thrust each on each side of the space shuttle, the SRBs. And why they have these at full length of the grain? Well, it's to effect a stable burn. For solid fuel rocket motors, you want to have a stable burn. Well, why does this have a stable burn? Well, first of all, you got to consider the ratio uh, um, of, of the total width of the fuel section grain is going to be divided into threes. Now, a good solid fuel rocket motor, one third, and one third. If you want to design a rocket motor This is not the determine the size of the nozzle. Determining the size of the nozzle is an entirely different dynamic. It's an entirely different set of calculations, and it is an entirely different subject matter for another day about designing nozzles for your rocket motor. But designing the grain, the fuel grain, the rule of thumb is you have a hole in the center. It's a center burner that's one third the diameter, total diameter of the fuel grain itself. So one third fuel grain on one side, one fuel grain on the other, and one third hole. Well, that's a cross section. So what do you have? You basically have a tube of fuel grain inside a tube of phenolics. Okay, that is this wall thickness is basically one third the total overall width, inner width between these two phenolic walls of the outer tube that serves as the casing that goes inside um, heat-treated anodized aluminum casing, which constitutes the fuel grain and RMS, which stands for reloadable motor system. So for designers, the rule of one third, in my opinion, is the most stable. If you want to go with 1/4, or if you want to go with 3/8, that's kind of up to you. 3/8 is 1/8 larger than 1/4, and that's in a fraction, and that can be converted to a percentage. One third can be converted into a percentage or can be converted into decimals. So fractions can be decimals or they can be percentages. These numbers can be represented in either three ways. Myself personally, I've made many rocket motors. Some blew up, some did not. But I use those 7 different stable formulas, which you can access and download off the internet. And my rule of thumb has always been one third, one third, one third. Now the motors might not burn as long, but I got to tell you, you're not going to have a motor that has high initial impulse and then burns out quickly or burns erratically. You mix the fuel properly, you pack it uniformly, you use common sense, facilities that are well ventilated, preferably non-residential and industrial area. And you have some training in mechanical engineering or chemical engineering. You have some experience with rocket motors. You can do this. I can teach you how to do it. I can teach you how to do it safely. In the state of California, it's probably not a good idea. Probably more open, Midwestern proper states like Nevada, Colorado, Utah, Arizona, where there's a lot of wide open space, nobody or nothing to burn down or hurt. Nobody to hurt, nothing to burn down. But my rule of thumb is for the motor grain itself, one third, one third, one third. So a tube of propellant, it basically has wall thickness one third overall width. Overall width, one third wall thickness, continues around a circle. Small circle in the middle is basically one third. So one third, one third, one third. Now, okay, so we're discussing the design aspects, and this is what I'm getting to. Burn time times pressure equals total impulse. Okay, again, burn time times pressure equals total impulse. Pressure is measured in NMs, Newton meters. I'm not sure if it's Newton meters or Newton mass. That's something I have to look up. I'm woefully ignorant on that kind of nonsense. I should know it as a rocket designer and builder. I'm ashamed of myself. I don't do that. That I don't know. Okay, but here's what I've always been thinking. Okay, there has to be a formula or an equation, and somebody's probably already thought of this, but I'm going to go ahead and think of it myself. When this fuel grain burns, this throat area right here in the middle of the fuel grain, that is considered the combustion chamber. It's considered the pressure chamber, the combustion chamber. That's where combustion takes place. The exhaust comes out the bottom through the nozzle, provides thrust for the first phase of a rocket's flight, which is the power-assisted phase, thrust phase, or launch phase, or under power phase, whatever you want to call it. As an engineer myself, I'm a hybrid monkey engineer, industrial design engineer. I wear many engineering hats. I'll call it whatever the heck I want. You can criticize me in the comments. By the way, leave a like, leave a subscribe. But this area right here, I know this is dry information, folks, but this is important This area here is the combustion chamber. This empty area here is the combustion chamber. Now, ablation of the fuel grain is the fuel grain burning, and it's diminishing in size because it burns from the surface all the way down to the inside of the empty to the inside of the phenolic casing. The kinetic casing and the rubber seals are high temperature. They're designed to handle uh, standard duration burn cycle for a standard non-experimental, non-extraordinarily unique or unusual or dangerous solid fuel rocket motor. Standard burn time is 5 seconds. And frankly, if you want a higher altitude, you put a bigger motor in a smaller rocket with less mass, less drag. That'll take off the pad a lot faster because it'll be under the power to weight ratio will be higher. So the thrust from the rocket motor can push the rocket off the pad faster. If you want lower altitude, you put a smaller motor in a larger rocket. The motor will burn, but it'll push the rocket less quickly off the pad, and that gives it only 5 seconds. The motor only has 5 seconds to burn either way, so its altitude depends on how quickly or how far it can push the rocket in 5 seconds, and how quickly it can push the rocket, or how far it can push the rocket in 5 seconds is determined by several factors, but most importantly, the weight of the rocket plus the coefficients of drag on all the rocket surfaces, including the nose cone, the body tube, the launch lug, the fins, etc., etc. So that's drawing in based on a hypothesis or based on the axiom, you built the rocket correctly, and it's not going to disintegrate in flight. And again, the 5 phases of a rocket's flight are powered flight, coast, apogee, descent, and recovery. So powered flight, coast, apogee, descent, and recovery. I don't want to draw a picture of that now. I've done that before. Those are the 5 phases of rocket's flight. And I'm just talking about things that are peripheral to this. Now, here's the crux of the discussion. And I'm going to, so this is the actual human being talking to you. I've been building rockets for 26 years now. What bothers me, or not what bothers me, or what troubles me, or what not even troubles me, what I'm curious about is no one talks about several things. I seem to be one of the only people that actually knows how to make a solid fuel rocket motor and do it safely. I'm one of the few people to talk about that. I seem to be the only person who actually builds my own customized field launch control units. I build them all day long. I sell them on eBay. I have one that's under construction right now. Some people seem to do it, but I seem to do it the best. But here's the thing: in the entire community of model rocketry, nobody seems to talk about the balance in the size of this combustion chamber. This combustion chamber's ability to maintain a constant pressure is based on its volume and its size. Now, what's interesting is the burn surface area. As this fuel ablates, the burn surface area increases. Now, follow me closely on it because this is the equation I'm trying to develop to explain this phenomenon. And I think it's true. And this is where I want, hi again, I want comments in the comments section that correct me and tell me if I'm a complete stoop. I'm an engineer, but I'm not perfect. Okay? I make mistakes. I'm imperfect. I don't walk on water. But I want to develop an equation that tells us that as the fuel grain ablates, the inner diameter gets larger, so the square area of the burning fuel grain increases. As it increases, more grain burns. Yet why doesn't the motor speed up as the grain gets consumed? It's because the area, the combustion chamber, the empty area increases as well. It requires more burning grain to pressurize it because its volume gets greater, because this diameter is decreasing and this diameter is increasing. So the burn surface area of the fuel grain increases because there's more of it. So there's more burning fuel contributing to the pressure in the combustion chamber, but at the same time, the size of the combustion chamber is increasing, so it needs that extra burn surface area. It needs that pressure and that extra burn surface area. Now, the reason I know the two balance each other out is because if everybody, including Aerotech, Cicerone Technologies, Apogee Components, Quest, and Estes, or anybody else who makes solid fuel rocket motors for the model rocketry community, nobody's ever had a problem with inconsistent burn rates as long as they use something called, like the smaller motors can have offset moon burners, which is an offset hole, or they can have slot burners. But most high-power rocket motors, the RMS systems, and not the single use, the RMS systems after an I-200, a J300, a K500, or an the infamous M1214 made by Aerotech, which is a fantastic motor and a popular selection for anybody who's trying to get their level 3 certification. Again, that's the Aerotech RMS M1214. It's a magnificent motor. It's very expensive, but anything Aerotech makes is definitely worth it. Very, very, very high quality manufacturers of high powered model rocketry goods. I recommend them too. So those guys also as well. This is going to be a core burner. Now I'm not sure if Aerotech, when they make their RMS, their reloads, I'm not sure if they obey the rule of threes. But me, again, as a designer, I like to keep things conservative and safe. I'll design the controllers, my launch controllers wild. I'll design the rockets wild. Airframes, parachutes, recovery systems, etc. But as far as motors are concerned, I'm very, very, very conservative. I had a very large motor blow up in my face. I'm lucky to be alive. It was a life-changing experience. It will never happen again. I have 7 major fuels that I use, and that is it. And some of them, 2 of the 7 fuels, are so dangerous I very, very rarely, if ever, use them. There's more types of fuels, but they're just too dangerous to mention. If I mention them, I generate a liability because they're dangerous. So we're not going to talk about how to make fuel grades. But I just wanted to mention the high-powered model rocket motor manufacturers community. Again, Cicerone Technologies, Aerotech, Quest, Estes, there's a few others. I don't know their names, but these guys are really good at what they do. You can check them out on Jacobs Rocketry. I highly recommend you visit Jacobs Rocketry. It's an absolutely fantastic website. You can also visit Aerotech's website, John Wickman's Space Camp in Wyoming. You can check that out too. Okay, but getting roundabout, this area right here, this fuel decreases, and then that because the diameter is bigger, there's more area of fuel burning. Well, that should create a greater pressure. It doesn't create a greater pressure because the empty area in the middle of the rocket motor, the combustion chamber, increased in size. Therefore, it simultaneously needs more fuel to maintain that same internal pressure. It pushes out the nozzle. It maintains that constant amount of volume and pressure out the nozzle, the exhaust volume, exhaust pressure at the nozzle, which creates the thrust. Again, total pressure of thrust times the amount of time the motor burns equals specific impulse. So time times pressure equals specific impulse of a motor. And again, we know standardized commercial manufactured model rocket motors, not mine, but most of them, 5-second standard burn time, just to be safe. Some of them have longer burn times, but I've got to be honest with you, you really need to know what you're doing if you handle those motors. Again, I'm in the process of developing, and I can't say that I know anything. I'm in the process of trying to develop a formula that explains the equality, the equilibrium between increase in burn surface area, and increase of amount of materials burning contributing to higher pressures, but that being equalized by the fact that the internal combustion chamber is growing larger, so it requires more pressure to pressurize. Now, I'm gonna if I get my way and somebody comments this, tells me I'm a complete fool, that's fine. I'm not going to argue with you. I've been thinking about this for a long time, but I'm not a mathematician. Of all the darndest things, I'm an industrial design engineer. We're a little bit different than regular engineers in that we actually step in the shop, we fabricate, and we build things without using a whole lot of math. We take a look at something, we figure out the basic principles of how something works. When we go into a machine shop, we start putting something together, fabricating from raw materials, and put something together that we think or hope works like what the customer wants. In my case, I love designing and building rockets. Not all my rockets work, I'll admit. Not all my rocket motors work either. I built deployment systems. They don't work that well either. Okay? And lately, I haven't had the money to do anything with rocketry except build a couple of experimental airframes, and I've gotten out of weather rockets. I have all my fuselage material for the weather rockets I'm trying to develop, 4 and 6 inch diameter material stored away in my closet. So I'm not doing much. So I'm kind of a hypocrite. But again, leave a comment. What is the formula that explains the equilibrium, the equalizing force, the increase in burn area as this motor is burning, contributing more material burning, contributing to greater pressure, but being equalized by the fact that the volume of the combustion chamber is increasing, therefore it requires that extra pressure. The two balance each other out and create constant thrust, pressure, and volume. Okay, so we can have pressure, very little volume. We can have a lot of volume, very little pressure, but both remain constant out of a core burner, standardized, commercially manufactured, reloadable motor systems, namely the fuel grains inside the reloadable motor systems itself. So, what is the formula that explains the equality between those two? The two equal each other out. They equal each other out perfectly. If they didn't, commercially available rocket motors, the ones that cost thousands of dollars, you have to wait a couple of weeks to get. You have to have a sponsor. The level 3 certification is a big political to do. Why is it those motors don't misbehave? Why do you get constant pressure out the nozzle? Even when you factor in ablation of the nozzles themselves, nozzles are very, very highly dense graphite material, not easily, not easy for heat damage. They hold up. They're very resilient, very resistant material. Why is it that the motor pressure, internal pressure of these motors remains constant? It's the equalizing and the increase in size of the combustion chamber that absorbs the extra surface area of material burning. The two equal each other out. Now, again, I don't know much about math. I would like to go down in model rocket history as the individual who comes up with a formula to explain that, a math formula. But you know what? I'm not that good at math. Somebody else out there is, and that's pretty much that. Now, my challenge to you, I'm going to turn the camera on me. Hold on. Okay. And by the way, this is not. Whoops. Hold on. By the way, this is not another episode of an Axe to Grind. I'm going to shoot myself. Oh, you can see some of my projects back there too. Actually, though, the other rocket, the one I am working on, the new motor system. Excuse me, you didn't see me do that. So this is what I'm trying to figure out. Again, one more time. Increase in surface area as the motor fuel burns should increase the pressure of the combustion chamber, the empty space core of a rocket motor, but the combustion chamber increases in diameter, so the two equalize each other out. Stable burn, stable pressure, and volume coming out the nozzle. The nozzle, you have an ablation factor of the nozzle, you got to factor that in. I'm kind of concerned. Maybe I need to work that into the equation as well. The ablation factor, dilation of the nozzle as the heat from the exhaust of the rocket's motor tends to eat away at the material, extreme heat. So what is the formula? Hey guys, you know what? If you beat me to the punch and come up with a formula, or you write in and say, Jason, you're a stoop, somebody came up with this and told Werner von Braun, or somebody told, what's that guy's name? Robert Goddard. I Geez, John Goddard or Robert Goddard? I don't know his guy's first name. The American early pioneer of liquid-fueled rocketry. Somebody told him, he got in touch with a mathematician. They figured the same thing out 100 years ago. I am astute, but it does indicate one thing. Great minds think alike. I hope. Uh, so this is where I ask you. You don't want to subscribe to the Rocket Minute. That's fine. On my other show, an Axe to Grind, which is this. This is not. I want to assure you. I tout the merits of free speech. As American citizens, this is kind of a crossover point between my two shows, an Axe to Grind and the Rocket Minute. Okay, I'm going to say it on both shows, folks, and we're at the 30-minute mark, so thank God. I'm not that good looking, and the material is dry, but I got to tell you, I'm going to stand next to every word. Okay, so I do know some things about rocketry. I've been doing it for 26 years. I'm still an amateur, but I do know some things, and some of the things I espoused on today, especially this math formula that I want to develop. I want somebody to comment and tell me about, hey, Jason, somebody already came up with that formula, developed by so-and-so, 50 to 100 years ago. So that's fine, but I want to know where to find the formula and apply it, because when I do move to another state, start building my own rocket motors, I'm planning on going either to Arizona or Nevada sometime in the next 2 to 5 years. I don't want to stay in California forever. You can't do anything in this state, including defend yourself from firearms. But that's an axe to grind. This is the rocket. Let's stay away from politics. But I do want to tout the merits of freedom of speech. Folks, a lot of people who are watching this video are American citizens. Do you have any idea how much trouble the founding fathers and the powers that be went through, how much trouble they went through to ensure that you have the right to freedom of speech, and as an American citizen, you have the right to access to information, you have the right to freedom of worship, relatively speaking, right, economic freedoms, etc., etc. Right to the freedom of the press, right to self-expression. If these rights were to be taken away, it would kind of be like developing asthma. All of a sudden, you'd have a problem doing something that you formerly took advantage of because it was almost an involuntary reflex. Freedom of speech can be taken away with a snap of the finger. The U.S. government is like any other government. Is run by people who can make decisions on the turn of a dime to reinstate or suspend certain rights and freedoms, depending on the political climate, or where they say or think they say war might be, or whatever. I have a hard time putting up with following the news. It's frankly that what's going on in the Middle East has been taking place for the last several thousand years. We're just agitating it by making Israel a protected state of this country. Again, I don't want to get political. This is not that thing. Okay? But folks, a lot of people, a lot of Americans, the founding fathers went through a great deal of trouble ensuring your right to freedom of speech. I'm exercising my right to freedom of speech now. I'm not really doing anything abusive, but at the same time, when's the last time you heard somebody tell you, leave a comment, subscribe, hit the like button? When's the last time you watched a vlog on YouTube like this one, or similar to something else, and someone said, leave a comment? And I don't see anybody leaving any comments. Every once in a while, somebody reacts to me leaving a comment about another blog. But I've gotten a lot of views, and I've started to figure out the formula for success in the other show, but I'm not getting any comments. Folks, like I said, freedom of speech is like like blinking your eyes or being able to breathe. If you suddenly develop asthma, you develop dry eyes, you have heart palpitations, some involuntary reflex in your body, your anatomy, starts to develop problems. Now you have to work at breathing. You have to work at blinking your eyes. Or you have to work at keeping your heartbeat. And you have to see a doctor. You have to have a pacemaker because that involuntary system is shut down. Again, we're all going to be real sorry if and when our right to free speech is suspended. I do have an axe to grind, and this is kind of a carryover from the other show. I'm not getting any comments. Folks, Do you know why YouTube is so popular? One of the reasons is the variety of information we get. The other reason is that anybody can post anything within reason and good taste, community guidelines, as they're called, within the YouTube community, which, by the way, I respect. Um, this is a platform, YouTube, YouTube Music, which I have like 30 different playlists. So I could be a music director at a radio station. I have good taste in music, at least I think. But YouTube is a platform for freedom of expression. YouTube welcomes and invites comments. You can watch a video and you can look at the comments of individual people who have their own channels. Now, YouTube has set things up where there are rules, there are community guidelines. There's not so much restrictions, but YouTube wants to maintain control. And I understand because, you know, even this sort of mechanism can be abused. It's not abusive to leave a comment. You're exercising your right to freedom of speech and freedom of expression and freedom of the press. Okay? So what I want, and I keep asking for in these videos, if you have the patience to watch this video all the way through, and we're at the 36-minute mark, exercise your right, your constitutional right as a U.S. citizen to leave a comment. All you have to do is just press the comment button and just say something real quick like, "Hi Jason, great video. Appreciate the point about freedom of speech." Okay. When I upload my videos, I do not censor or filter anything. You are free to say as much as you want, when and how you want, about anything you want. I don't restrict other people's right to freedom of speech, or freedom of expression. Do you know why? Because a lot of people have very strong opinions about a lot of things. And the reason a lot of people have very strong opinions about a lot of things is because they're very, very experienced in life. What I understand about the human condition is this. What you go through and experience in life has a lot to do with shaping who you are as a human being and how you express yourself. Everybody in the world has a reason for their opinions. Everybody in the world has a reason for saying what they say, when and how they say it. Okay? It may not be right, it may not be wrong. It doesn't matter. I want to interact with you. I want you to interact with me. I call it the teacher in me because I like teaching people as well. I love teaching. Okay? With your freedom of speech, take advantage of the opportunity before, if and when, and before it maybe might get taken away from you. The U.S. government has already launched an assault on TikTok, which I'm absolutely shocked they'd have the nerve to do something like that. TikTok is a platform for freedom of expression to a little bit more of an extreme degree than YouTube. YouTube is a little bit more conservative, a few more restrictions, a little bit more censorship, more geared towards the family, but some extreme shows come on as well, and there's some scary stuff on YouTube as well. Scoops is another platform that's about one more notch to the uncensored and wild and uncontrolled than even TikTok is. And if you're able to stomach some of the stuff that's on Scoops, I would say it's a lot closer to unrestricted, uncensored form of self-expression and the ugly side of life, things that actually happen. Because real life, sometimes it's PG, sometimes it's PG-13, a lot of times it's rated R, but nobody's going to protect you from real life, and nobody bothers to give real life ratings. So there you go, 1, 2, 3. YouTube, TikTok, and Scoops in that order. And I watch all three, and I like to post my video on all three. But again, you have a right to freedom of speech. Please leave a comment. Just say anything. I want to hear something, somebody say something. Leave a comment on this show. Leave a comment on the material I talked about. You watch the video, watch it all the way through, or watch it halfway through. Leave a comment saying, "Geez, this is boring, Jason. When the hell are you going to launch rockets? I've been talking about rockets for 8 years. One of these days I will, and I've got one in my vehicle that's pretty darn close to being launched. I've got to finish it up. It's a single-engine rocket. It's a very conservative design. I'll share that with you guys the next time I shoot another video of the Rocket Minute. In the meantime, we're at the 40-minute mark. Thanks for staying with me as long as you have. Tune in, don't tune out, and turn up the volume and express yourself. Exercise your right to freedom of speech and say something. Say anything. Because if you don't stand for something, you will fall for anything. The other thing is, don't let other people think for you. You need to exercise your right to freedom of thought. You're a free will agent. You were designed that way. Think for yourself. Okay, my name is Jason Wampler. I'm the host. It's been another episode of the Rocket Minute. And hit the like, hit the subscribe, leave a comment.